Hey everybody, welcome to Studio 64. My name's David. I've been searching the interzones for some more science, space and tech news to share with you, and I came across this over at Indy 100. This should be interesting. Origins of rocks that built the first continents discovered. Okay. Yeah, so I'm not a scientist myself. If any geologists want to weigh in, please feel free to comment down below. I'd love to hear from you. I love this strata. Just to think that I believe this is correct. Each layer of those is a period in history, like the rings of a tree, the age of a tree. It's a similar idea, but this is over thousands and thousands and tens of thousands and possibly even millions of years. Imagine the stories, who animals and plant life, and as it become closer to our time, humans walked on these individual layers. That's fascinating. The stories, just unbelievable. It's incredible. Yeah, well, a new study suggests that 3 types of coarse-grained rocks could be attributed to the first continents emerging about 3.5 billion years ago. Now, once the oceans cooled and developed on Earth, it was almost all that was there. The land was restricted to small volcanic islands, which have since eroded away. And as usual, I'll leave the link to the main article below the video, so you can pop in, check out these embedded links. You can go for a bit of a deeper dive beyond the main article if you want. Makes for a very interesting read, believe me. Now, we do know that parts of early continents have survived in Western Australia, northern Canada and Greenland. These pieces gradually expanded to the continents we know now. Now, while other continents formed millions or billions of years later. However, geologists have been perplexed by how the first crust was formed, particularly in regard to whether plate tectonics were involved. Due to the first crust forming billions of years ago, this means it's hard to identify individual nature. Interesting. But Dr. Matthias Schmidt and colleagues at the University of British Columbia claim to have done this. We tracked a specific set of trace elements that aren't affected by alteration and pristinely preserved signatures from the original magma, Schmidt said in a statement. The ratios of these elements are considered crucial to understand how these continents emerged. Now, collectively known as TTG, the original crust was composed of 3 types of rock: tonalite, trondhjemite, and granodiorite. Schmidt and colleagues analysed materials collected worldwide to find commonalities rather than previous studies that have looked at samples from only one or a few locations. Oh, cool. That's pretty good. Yeah, so all over the world as opposed to, 1 or 2. Fascinating. As I say, I'm a student of all science. I love all science. I love reading these articles and just sharing them with everybody because it just amazes me. No matter what kind of science it is, archaeology, geology, astrophysics. Speaking of that, are there any astronomers out there, astrophysicists or astrogeologists, looking at stuff like geology here on Earth? Do you think that similar plate tectonic type things, see, I don't even know, that's how professional I am at this, science, depending on the world, say moons around Saturn and Jupiter, do you think they could develop their own plate tectonics, or are they too small, or is it possible? Having, different conditions on that planet, how different do you think they would look compared to ours? It's just a thought. They're volcanoes, different to ours. How would that affect their plate tectonics? Fascinating. Yes, here we go. These elements allowed us to look back through the chemical changes that TTG magmas go through and trace the melt compositions back to their initial state and source, Schmidt added. The authors of the study, published in the journal Nature Communications, have proposed a process that would help explain the formation of the older segments of continents which have become their backbones. This is intensely interesting. All these rocks, and especially their combination, can be explained by the model we present, Schmidt claimed. Ours is a simple model in which TTGs, as well as the younger rocks that TTGs are typically associated with, resulted from the slow burial, thickening and melting of precursor crust that likely resembled oceanic plateaus. Now, the continental crust was destined to develop the way it did because it kept getting buried further and further. The rocks at its base had no choice but to melt. In doing so, they made the TTGs that proved a winning recipe for continental survival and growth. Temperatures probably exceeded 1600 degrees C to 2900 Fahrenheit under all the material. Yeah, again, interesting. What would it be like on a planet like Venus or something like that? That'd be interesting. Did that have active volcanoes? Yeah, really interesting. And the moon, we know had active volcanoes on it, definitely further away than last week. We know that they were on Mars at one point. It's just fascinating to me. I wonder what the differences would be. Climate, size of planet, type of rock. Yeah, interesting. If the model withstands scrutiny, it has the potential to address a long-standing issue for geologists. Previous models have proposed that TTGs were formed after plate tectonics began in the first subduction zones. However, there is uncertainty on the timing of plate tectonics' origins, and some suspicions imply that it's younger than the first continents, resulting in an evident problem. Now, there's always been a chicken and egg question of which came first, the start of plate tectonics of TTG magmatism to make new continental crust, Schmidt said. We show that these things may actually not be directly related. The recognition of the type of source rock makes this leap possible and also takes away the need to have other mechanisms such as meteorite impact explain the growth of the first real continents. Interesting. I'm just curious about how that would impact on the say the dinosaurs, if there's just something that we could loop into the picture. Yeah. So a meteorite impact with the dinosaurs. Say there was no meteorite impact. So it also takes away the need. Could that be a possibility? Could there be a possibility that, if we take a meteorite impact into this, was this at the same time as the dinosaurs? Somebody let me know. Maybe what took out the dinosaurs if it wasn't a meteorite impact? Again, I could be completely wrong. Just talking about my out my side of my mouth here at the moment. So, just a thought. Now, while TTG only makes up a minority of the Earth, the parts of it are still a big part of North America in particular. Now, Schmidt pointed out the humour that many people have varieties of this type of rock as a kitchen countertop. In a way, many people are preparing their dinner on the type of rock that was responsible for making our modern continents. It's interesting. And unfortunately, with most modern homes, there wouldn't be I'm assuming there wouldn't be a great deal of conversation around the origins of these rocks. No, of course not. Yes. Fascinating, isn't it? All right, well, my name is David. Thanks for joining me for another Studio 64 Science, Space and Tech News update. I shall see you in the next one. If you enjoyed this video, please like, share, subscribe. Greatly appreciate it. If you're up for it, drop a comment down below the video because I'd love to hear what you think. All right, take care, and as I always say, if you can't be good at it. And as I also always say,
I'll be back.